Hello everyone and welcome back to On the Spot STEM. Today we'll be doing a video on square root decomposition of a tree. So I'll explain how regular square root decomposition works first, and I'll explain then how we can use it on a tree. But this is a pretty powerful technique on USICO, and basically it can be used on a lot of USICO tree problems where you want to do updates on a range from I to j, where I and j are nodes in a tree, or you want to query something along a path from I to j. And it's one of those techniques where you can, if you have a problem like that, which I just described, you can usually throw this algorithm at it, and it's a lot more efficient to implement than using something like heavy light decomposition, which requires knowledge of segment trees, and you have to code it on a tree, which is kind of unintuitive, and it gets the implementation is a lot more annoying to do than it is for square root decomposition, which is very light compared to that. So, if you don't know what square root decomposition is, I recommend you check it out in another video on YouTube or find an article about it online, because I'm just going to explain it briefly here and its main topic. But essentially, if you have an array in regular square root decomposition, you might have an array, let's just say it has 9 elements, but it doesn't have to be a square number. So you have your 9 elements. Let's just say they're filled with like these random numbers. Okay, and so what you do in square root decomposition is you break this up into chunks. So your first chunk would be from your 0th element to your 2nd element, or from essentially 1 to 3. Your second chunk would be from your 4th to 6th. And your third chunk would be from your 7th to 9th. And what you want to do is you have k chunks, each of length n over k. And when you're doing queries, you're going to be using n over k and k. So if you want to minimize k plus n over k, this happens when k squared equals n, or k is approximately root n. And you just take the ceiling of this value for your chunk size. So let's say we have a bunch of queries of the form L to R, where L is your left endpoint and R is your right endpoint. For example, we might have a query asking from 2 to 7. And for each query here, we want to find the sum. So normally what you could do is you could just loop from L to R, and then you'd have to, that would be O of n essentially, since you could go through at most n elements. And you have q queries, let's say. So this would be O of n times O of q, which is equal to O of nq. If n and q are both of the order 10 to the 5th, this is way too slow for contests. So we want to find a way to optimize on that. And if you have to do, and updates here are O of 1, so that's not a problem. But let's try to find a way to optimize that using our chunk method. So we broke our thing up into chunks, so I'll just put them here. So our first chunk is 3, 4, and 5. Our second chunk is 8, 7, 12. And our third chunk is 15, 17, 23. Now let's say we want it to go as our sample query from 2 to 7. So this is our second value, and this is our 7th value. So essentially what we do is, since it's L and R are far enough apart, we're going to be going through like something close to n elements. But a lot of these chunks, we're not going to be going through part of them. We're going to be going through the whole chunk. So we're going to be going maybe from L to the end of our chunk, which contains L. Then we'll be going through this chunk, this chunk, this chunk, this chunk, and so on until we reach another chunk, and then we go from this to R. And these sizes are very small, and there are some amount of chunks which we can just compute in O of 1 time. So I'll just demonstrate what I mean. When we're going from 2 to 7, we go from 2 to 3, and let's say we want to find the sum of these numbers, so we go 4, then we add 5. Then this entire block will be gone through when we go from 2 to 7, so we just add block 2. And we can store these values in another array, which is of length square root n, and then we go just plus 50. And so this is equal to 9 plus block 2, which is 27, plus 15, which is equal to 51. Now let's say we wanted to do an update on this. So let's say we updated this value over here to 10. And let's say our values in these blocks were of 12. Now this update is just O of 1 since we just have, or this is O of root n, since we just have to sum this entire block again. So the new sum is 30. And you can actually do this in O of 1 since you're just adding the difference of your value from your old value. And then this sum is over here is equal to 15 plus 17 plus 23, which is 55. So if we go from 2 to 7 again, we just go 4 plus 5 plus block 2 plus 15, which is equal to this time 9 plus 30 plus 15, which is equal to 54. And so let's just analyze the time complexity of this approach. Basically, when you're going from L to the end of your block that contains L, that's at most square root of n times. Then you're going through at most square root of n blocks. We're computing each of these sums in O of 1 since we pre-computed them. And then we're going at most square root n elements from our last block, or from the block that contains R to R, because each block length is at most root n. So this is equal to O of root n for single query. And we have Q queries. So it's equal to O of Q root n. And this is simple enough to pass because if they're both 10 to the 5th, then Q times root n is equal to 10 to the 7 times about 3.15 or something. And that's well enough to pass in contests. So you could do this for just queries, and you can also update stuff. Updating just a single element would take O of 1. If you're updating a whole range, basically all you have to do is you go from L to the end of your range, you update each of those elements, and you can find that new sum. And then when you're going through all these blocks in between, you can basically create a lazy counter, and you can increment that lazy counter. So if we're adding 2 to all these elements, this will become from 2 to 7, this will become 6, this will become 7, and then this will become, this second block, we're going to go through the whole thing, so we're not like just accessing some values from it. So our lazy counter here would be 2 now, which means that we're adding 2 to every element of this block. Since there are 3 elements in the block, our new sum essentially would be 30 plus 2 times 3, which is 36. And these values, we don't actually have to update them because we know we just want the sum, but I'll just put it here for brevity. And then we just update this value over here. And so we're going from L to the end of the block, which is again square root of n. We're incrementing a lazy counter to at most root n blocks, and incrementing a counter is just O of 1 time. And then we're going at most square root of n elements when we're updating to the right input. So that's again O of square root n for an update. And then if you have 2 updates where they're both bound by 10 to the 5th, then that still passes within time. So as you can see, this approach is very intuitive too, and it's pretty simple to implement. You just find your block size, and then you just separate them, and you just have to find L to the end of the Lth block. Then you just go through your other blocks, and it's pretty simple in general. So that's for an array, but how can we do this on a tree? A lot of USICO problems are designed such that you have a tree, and you're gonna have Q queries where you go from I to J, and you do something along this path, or you might have to return something along the path, and then after that you return values, and you might be updating elements or whatever in this. So how can we do this on a tree? Well, I'll show you guys how to do this when walking through an example problem. So this is USICO 2015 December Platinum number 1. And so I'll show you how to do this. So the problem reads, Farmer John has installed a new system of n-1 pipes to transport milk between the n stalls in his barn, which are conveniently numbered 1 through n, and n is bound by 50,000. Each pipe connects a pair of stalls, and all stalls are connected to each other via paths of pipes. So it's just a tree, which everything is connected. FJ is pumping milk between k pairs of stalls, where 1 is less than or equal to k, less than or equal to 100,000. For the ith such pair, you are told 2 stalls, Si and Ti, which are endpoints of a path along which milk is being pumped at a unit rate. FJ is concerned that some stalls might end up overwhelmed with all the milk being pumped through them, since a stall can serve as a waypoint along many of the k paths along which milk is being pumped. Please help him determine the maximum amount of milk being pumped through any stall. If milk is being pumped along a path from Si to Ti, then it counts as being pumped through the endpoint stalls Si and Ti, as well as through every stall along the path between them. And so the first line of the input contains n and k. The next n-1 lines each contain two integers x and y, describing a pipe between stalls x and y, and the next k lines contain s and t, which are describing the endpoint stalls of a path through which milk is being pumped. So I'll go through the sample input. And so you have 5 vertices in your tree, and the tree looks like this. Essentially, 1 is connected to 5 here, and then 5 is connected to 4, 4 is connected to 2, and then 4 is connected to 3. So this is the end of your tree input. And then we have these bunch of update operations, essentially. So in our first thing, we're going from 5 to 4, so we can add 1 to each of these. And then we're going from 5 to 4 again. So we can make each of these 2. Then we're going 3 to 5. So we go from 3, then we go 4, then we go 5. So this becomes 1 and each of these becomes 3. And then we go from 4 to 3. So that goes 4 and then 3. So this becomes a 4 and this becomes a 2. And then we go 4 to 3 again. So this will become a 3. This will become a 5. Since we've gone through it 5 times. And then we go 1 to 3, so that's 1, 5, 4, 3. So this becomes 1, this becomes 4, this becomes 6, and then this becomes 4. Then we go 3 to 5, so that's 3, 4, 5. So this becomes 5, this becomes 7, and this becomes 5. Then we go 5 to 4. So this becomes 6, this becomes 8. Then we go 1 to 5, so this becomes 2, and then this becomes 7. Then we go 3 to 4, 3, 4, so this becomes 6, and this becomes 9. And so the maximum number of times anything was pumped through is 9, and that's 4 over here, so that's why we return. And so basically what you can do, your first instinct might be just to do this for each thing. For each of these k updates, you just go from I to j. And how you can simulate going through I to j quickly is to find the LCA, which is the least common ancestor, or it's just the lowest, it's basically like the topmost point on the path from I to j. So if we're going from 3 to 2, then our topmost path is 4. And then we can basically break up our query from 3 to 4 and then from 2 to 4, because that's the same thing as going from 3 to 2. And so we're doing this k times, and essentially simulating, adding 1 to each of these values along each path would be essentially, if our path can be up to length n, if the tree is a line and we go from 1 to n, our path is of length order of n. So this is O of k times n time, the naive approach. And if k and n are both 10 to the 5th, or their orders of 10 to the 5, this is 10 to the 4 times 5, and this is 10 to the 5th. This would be essentially over 10 to the 9 operations. And that's way too much for what we're trying to do here. So we have to find a way to break this up. And you can probably draw some similarities between this and the square root approach I was explaining earlier on the array. In the array approach, the naive approach was to go from L to R and update every value. But what we saw was that we can break this up into blocks, and we can just go through a block efficiently to make our thing O of root n. So how can we do this on a tree? The defining elements of our array approach were that when going from I to j, we'd break this up, or from L to R. We'd go from L to the end of the block, the end of the block, and then we'd go through a bunch of blocks. And then we go from our sequence to R, so last block to R. So we want to somehow relate that to what we're trying to do on a tree. And so basically what we're doing in a tree is that if you look at the problem, what we're essentially doing in each of these k things is we're given 2 numbers, and we update every value by 1, we add every value by 1 on the path between those 2 numbers. So if we're going from 30 to 5, we update every value in this path from 30 to 5. And Now this is, if we just try to apply our array approach over here, this is pretty hard because when we're going from 30 to 5, we're going up and then we're going down. So if we go up and then down, it's kind of hard to go through the end of the block and then like circle around the block. So what we can do instead of doing that is we can break this up into two separate updates. Each of these will have two separate updates when we go from I to j. So we break this up into this kind of chain, and we break it up into this kind of chain. And this point, this is called the LCA, and it's the least common ancestor of these two nodes. And we can actually find the LCA in square root of n time. And I won't talk about it right now, but I'll talk about it more when I'm discussing my code. But essentially, the idea is that the LCA, it's going to lie, if you have two nodes, the LCA, if you bring this up to the same depth as this, the LCA is going to be in the same block as these two nodes. And so, once you do that, or once you bring it up over here, you can bring these two up fast to the same block as the LCA, and then you can just go up the block. So that'll just be square root of n time to find the LCA. But now that we are going through a chain to the LCA, and then we're going through another chain to the LCA, this looks a lot like our array approach. If you rotate this horizontally, actually, you can see that this is a lot going like from left to right, or from right to left. So similar to our array approach, we want to decompose this tree into these types of chains and into these types of blocks. And then we can just update each block quickly. So to do this, if we're going from 30 to 1, first of all, we can define our block size as b. And if the height of the tree is h, we just want b equals square root of h. And as h goes to n, b will be basically root n. But h won't always be equal to n since h is usually smaller. But if we make our block size the square root of the height of the tree, which we can compute using just a DFS, then essentially when we're going from a number to the LCA of these two nodes, we go from that number to the end of the block. And when we go from this number to the end of the block, we can have a values array, okay? So this values array will store the number of times we went through a node. And so when you go from 30 to 1, we'll go 30. So values of 30 will be added by 1. Values of 25 will be added by 1. And then we jump up here. And then now, if our tree is big enough, we're going to be going through many blocks or many chains at a time. Like if we had like 10,000 nodes, then we'd be going maybe like 100 blocks or even like 300 blocks each time, because that's square root of 10,000. So if we go through all the values in each block, that's the same thing as going through all like almost 10,000 elements each time if the chain is big enough. And that's not good because that would be the same thing as going O of k times n. So since we're breaking this up into blocks, we want to do something similar to the array. And remember what we did in the array here. We had a lazy counter. Essentially, when we were updating our values from L to R, if we went through an entire block, instead of updating each value individually in the block, we just kept a lazy counter for each block, and we updated that lazy counter instead. So we can do something similar here. When we're going from 30, well, when we go 30, and then we go 25, and we're at the top of this block, when we jump to the next block, we know we're going through the whole block entirely. So we can just keep a lazy value at 21. And we can add a lazy value to 21. And so this value means that we're adding 1 to 21. We're going to add 1 to 21's parent, and we're going to add 1 to 21's parent's parents. And we add 1 essentially until we reach the top of the block. But we're not going to add 1 right away. We're only going to add that at the end. Or we're going to add how many ever times we've queried this. Because if we do it right away, that's the same thing as going through the whole block. So we keep this lazy value of 1 and we go up to here. And then we go to 6. And since 6 is in the same block as the LCA, we can just go again and add 1 to each of these nodes. And this is just from one point to the LCA, and we do the same thing from the other point to the LCA. So what's the time complexity of this? Well, when we're going from our very downward point to the end of its block, that's at most O of b, which is O square root of h time. Then we're going to be going through a bunch of blocks, and we're going to have at most square root of h blocks, since the height of the tree is h, and each depth is square root of h. So h over square root of h is square root of h. So we're going through at most square root of h blocks, and incrementing our lazy value by 1, we can have a lazy array. Incrementing that value by 1 in each block is just an O of 1 operation if it's an array. And then when we go to the top of this block, to the LCA, or just that topmost point, we're traversing at most through another block, so that'd be another square root of h at most. And that's equal to O of root h. So that's our update for one time, and we're going to do this for 2 things each time, since we go from 30 to LCA and then 5 to LCA, so we're doing this twice essentially. So it's essentially O of 2 root h, which is still O of root h. Now, how many times are we doing this? Well, we're doing this for each value over here, each pair, and we're doing that k times. So we just multiply by O of k to get an O of k root h solution. And this is equal to O of k root n, because h is bounded by n. Once again, this is very similar to our block thing in which we went O of q root n. So O of k root n, if k is 10 to the 5th, and n is like 5 times 10 to the 4th, I believe this comes out to be about like 2.2 times 10 to the 7, which is, and this is multiplied by a constant factor of course, but this is good enough to pass within time. It's not 10 to the 10 as our naive approach was. So now that we found this method, we essentially created a framework to go through our thing. What we do is that for each query, or for each update, and we have k updates, we find LCA of the 2 numbers I'll call them A and B. So we update A to LCA, and then we will update B to LCA, because this is 30 to 1 and then 5 to 1. And then we do this k times, and at the very end, when we're finding the number of times that a point has been through, we can also increment the lazy values back here. So let's just present the lazy value at 21 was 4. Let's say this block was traversed a total of 4 times. Then we'd add 4 to the value at 21, then 4 to the value at 15, and 4 to the value at 11. And we're doing this at the very end. And so what's the time complexity of adding our lazy values? Well, it's just the length of the block, and each length of the block is root h. And how many times do we have to do this? Well, we have to do this at most of an order of n times, because of all these nodes over here. At the bottom of each block, that's how many times we're incrementing a lazy value. So it's just O of root h times n, which is to do our final thing. And so this is the complexity of doing all our updates, and this is the complexity of adding all our values at the very end, and then we just take the maximum of the values that are in the tree. And so overall, this becomes O of k plus n root n. And that is also fast enough to pass. So now I'll go over my code for the problem, and I'll explain line by line what each step does, and I'll try to clarify any confusing things in the code. Okay, so now I'll go over my code for this problem. So over here, all we have is just our variables that we're going to be using. And this is basically our representation of a tree. It's an adjacency array list. This is the depth of each node. This is the parent of each node. This is the jump parent of each node, which is basically if you have a node, it just goes to the next block. So in our diagram over here, the jump parent for 25 is 21. The jump parent for 30 is 21. And the jump parent of 35 is 21, because that's basically it's the next block on the way to the top. And then we have our values here, and we have our lazy, which is just, again, a way of being efficient about updating a whole block at a time. So we have our input-output over here. Then we have our array list representation of the tree initialized. And this is just initializing that for the first n-1 values. Then we initialize our values, our lazy, and our depth. Over here, what we have is just BFS to calculate the depth of each node. And then we have the parent, we have our jump parent, and then we'll initialize those. And so they're initialized from this function. So this BFS also calculates the maximum height of the tree because we want our thing to be O square root of height, ideally. So when we initialize with our height over here, we'll just set the block size, which is the size of each block, to be the square root of the height. And then we'll run a DFS from the first node. And I'm using 1 indexing here. I'm not using 0 indexing. So in our DFS, what we just do is we calculate the parent. And then if we see, since the block size is defined as the size of the block, if the depth of the node is equal to 0 mod the block size, then we can set the jump parent to be that. Otherwise, we just set it to the jump parent of its previous thing, which is its parent. So over here are the main methods that we're going to be doing. So from 1 to k, we essentially this is our other part of the input. We take 2 integers at each point, and then we have to update the path between those 2 integers. So first, we have to find the least common ancestor, which again is just the top of it's just the node that's the top of their path. So again, if you go from like 30 to 5, their LCA is 1. If you go from 18 to 15, then their LCA would be 6, since you're going like this. So we can find that in square root of n time, and you can also actually optimize that to find it in log n time, but I'm not explaining that here. So this is just the way to find our LCA in square root of time. And basically, what we want to do is the LCA is, we want to move U and V up until they're in the same block essentially. So at each step, we can go to the next block that's above them. And if they're in the same block, meaning that their jump parent is the same, then we can just go to the LCA in the same block. And if we're just assuming that depth V is greater than depth U, so we can swap that if it's not true. And then we'll set V equals jump parent V to go up like that. And then if they're both in the same block, this is very easy to simulate. If they're the same node, then we'll just return U. And if the depth of U is higher, then we'll just set that equal to each other, or we'll swap them. And then we'll set V equals parent V. So essentially, we're just moving up each of them one step at a time. And since they're in the same block by this function, it's at most root h moved up. So this is root h complexity. And when we're jumping from a block while they're not the same, we'll jump up at most square root of h blocks. So this is also square root of h complexity. So now here's our update function. Essentially, as I said earlier, we're going to be updating from the node to the LCA of that query. So if they're in the same block, which is if the jump parents are the same, then we'll just update in the same block. Otherwise, we'll move our bottom node, to the top of the block where it's in. So while it's not equal to the thing in the next block, and then we'll just update this block. As I said earlier, we updated 30 first, and then we updated 25. So that's essentially what this is doing here. It just updates the value at the bottommost thing, and then it'll move it up. And if it's now at the top of the block, then we'll break out of this function. And then, when our 30 goes to 21, which is at the bottom of the next block, as we saw, we can just jump up blocks at a time until it's in the same block as the LCA. So that's what this part does over here. And then, as I said earlier, we'll be using a lazy counter to just show that we're not updating all these values at once, but we'll store it at the bottom value and then update those later. So we're just incrementing this lazy counter, and then we're going to move a block up. And then once they're in the same block, we can naively simulate this again, because if they're in the same block, we'll go up at most square root of h nodes. So while this is not the LCA, we'll just increment the value here, and we'll set it to the parent. And then when it reaches the LCA, we'll also increment the LCA. So what we're doing at each step from 0 to k, or from 1 to k, we're taking our 2 nodes that we're going to be updating the path between. We find their LCA. This is a square root of h operation, which is square root of n. Then we'll update a to LCA and b to LCA. And the update functions are each square root of n time, or square root of h time. Because over here, we're going to be essentially jumping to the top of the block, which is square root of h, and then we'll be jumping blocks one at a time, and they're square root of h blocks. So this is at most square root of h, and if they're in the same block, we're moving at most square root of h nodes to the LCA. So this is also a square root of h kind of function. And then I'm just decrementing val's LCA by 1, because when we're going from a to the LCA, we're incrementing the LCA by 1. When we're going from b to LCA, we're also incrementing LCA by 1, so we have to, since we're essentially counting that twice, so we have to decrement that by 1 in order to solve that. So this is what our main method does. And then after that, we just have to put the lazy values back into our tree. And then, so basically, we run a loop from 1 to n. And if the lazy value is greater than 0, meaning that you have to update its block, then we'll just update the lazy value there. And we'll set the lazy value to 0 because we're done with it. And so this is our update lazy function. And so our x over here is essentially the bottom of a block. So while x is not equal to jump parent x, so while it's not equal to the value in the next block, so just staying in the same block, we'll add lazy to this value, and then we'll just send it to its parent. And then we'll add lazy to the parent, so that's why we have this lazy value here, and then we'll send it to its parent. And once we reach the next block, we'll end, because we know the lazy value only stores it in for the block. So that's pretty much all. Once we update the lazy for each, we can just find the maximum of each value, and then we'll print that, and then we're done. So to recap, what we did was, we saw that similar to an array, you can break this up into 2 chains for each update, and you can decompose the tree into blocks, sizes of block root h, and then when you're going from a node to its LCA, you can either go through a full block, which we can just increment our lazy value by 1, and we just go through square root of h blocks, so that's square root of h, O square root of h update, or we'll just go from a node to the very next block, which is also square root of h nodes or less. So, and then if you just analyze this, it'll come to O of k plus n, root n complexity, which falls under time. So I'll show you how that works now. And yeah, so it looks like it's a bit tight on time, but it's actually like just fine, because it still falls under the time constraints since it's a square root of n approach. And once again, this kind of approach can be optimized to a lot of problems involving trees where you have updates on from I to j, which are nodes. And you can actually solve this year's goal number 2, the 2019 December goal number 2, using this approach, where you store a hash set from each node to the top of the block. And if you want more details on that, I can write it in a comment. So thank you for watching, that's all. I hope you understand square root decomposition better now, because it may seem pretty tricky at first, but when you compare it to other methods, such as heavy light decomposition or some other like method that's hard to implement, this seems a lot more lighter to implement, and it's a lot more intuitive to implement also. So thank you for watching. If you enjoyed this video, please let your friends, family, other people know about this channel, because we're almost at 1,000 subs, and Happy New Year. Thank you.